Hi, my name is Joshua Joseph, and this is my Physics 2211 Lab 2. So in this lab, the purpose was of observing the effect of gravity and drag force on the motion of the tennis ball being dropped from a certain height at rest. And in this lab, unbalanced forces are acting on the ball, causing acceleration. In this lab, we're going to be focusing on Newton's second law, primarily the momentum principle, and the summary results state that when comparing the three different data sets, it can be noted that the data points between the observed data and the computational model, including the drag force, are a lot more similar compared to the computational model which doesn't include drag force. So when we're looking at the free body diagram, initially when the ball velocity is less than terminal velocity, drag force is pointing in the opposite direction than gravity, but is smaller. But when ball velocity equals terminal velocity, both drag force and gravitational force are equal in an opposite directions, canceling out. So the formulas that we're going to be using are the velocity update formula, v initial plus f net over mass times delta t, position update was position initial plus v velocity average times delta t. We're also dealing with force of gravity, so f equals negative mg, where g is 9.801. And then drag force, which is a force equals to negative b times v instant squared, and b in this case is going to be a proportionality constant. We will look into that later. So let's quickly look at the the tracker. As we can see here, as I have tracked the points as the ball continues to fall down, and we can see the time as well as the Y position on the right hand side. So let's look at the computational model. The first one is going to be without including the drag force. And so here I updated the ball's mass as for the average tennis ball mass, and also the position and velocity vectors to be 0, 0, 0 in all directions. I also updated delta TB to a 1 over 60 for the frame rate of the video. And since we're not dealing with drag force, B is equal to 0. And I also updated the time in this time to match up with the video, and updated the net force where, since we're only dealing with gravity, it's going to be negative m times g in the direction. We also have the updated velocity and position formulas here, and it prints out the time and the ball's position in the y direction. So when we run this program, we'll see the ball shows a similar motion as observed in the video as well. And here are the data points. So let's quickly look at the computational model, which does include the drag force. So everything is relatively the same except for a few changes, where here um, the B, the proportionality constant, is going to be 0.003. And I determined this through trial and error until the computational model finally was relatively close to the observed data. And I also had to update the net force to include the drag force. So in this case, W is going to be the weight force, and that's going to be negative m times g in the direction. Then FD is going to be the force due to drag, which is going to be the B times the magnitude of the ball's instantaneous velocity squared, and then in the direction as well. And then we're going to add these two up, and we print the values of time in the y position. And when we run the program, we're able to see a similar function movement of the ball as well as the time. So let's quickly look at the Excel and compare these three data points. So when comparing it, we can see the blue, which is going to be the experimental. The gray is going to be a computational 2, which includes the drag force, and orange is going to be computational 1, which does not include drag force. As you can see, around the beginning, they're all relatively close to each other. But as we continue further away, um, the experimental and the computational model, including drag force, start to veer away from the computational one that does not include drag force. And so, what are some possible errors that occurred? When I was tracking the ball, it was obviously hand tracked, so there's obviously slight deviations from the actual data. The B value was also determined through trial and error, so that might also lead to another skewness in the data. Another thing was the video that I recorded for the tracker might not have been long enough to determine the true effects of drag force, and so we weren't able to get the true effects of drag force acting on the ball, which affected the velocity from there. So what does it mean? So in the what does it mean question is asking about terminal velocity and which computational model will predict that. And only the second computational model will predict terminal velocity, since it's the only one that accounts for drag force. And like I said before, terminal velocity is when drag force and gravitational force are equal in opposite direction. And the what if scenario is if we threw the ball initially down, would this affect terminal velocity? And no, because terminal velocity, as I said before, is only based on the drag force and the gravitational force being equal and opposite. So the conclusion is that after comparing the observational data with computational data, found out that computational data that did include the drag force was more accurate and more similar to the observed data. Thank you.